Hello, my name is Aidan Friedrich, and this is my review on increased tumor homing and tissue penetration of the filamentous plant viro nanoparticle potato virus X. So, a bit of background. Nanoparticles are a big field currently, and they're very prized because you can basically add whatever you want to them, and then these nanoparticles are easily able to traverse the body without too much immune response. And the things that you can add to them is shown on the right here. Is you can add like antibodies so that they target a specific thing. You can add fluorescent dyes so that you know where they end up. You can add DNA so that they end up transcribing or tricking the cell to transcribe certain things. And these ligands can all be added so that they can be specifically targeted towards a certain part of the body. Now, filamentous nanoparticles have shown increased pharmacokinetic movement, that's just movement through the body, as well as tumor homing properties, so they end up being able to find the tumor in the body and specifically go into that tumor a lot better than the spherical nanoparticles that a lot of people think of. These filamentous nanoparticles are more like rods, almost like kind of like what bacteria looks like. And currently, a lot of the development is in these spherical nanoparticles because they were the first ones to really come out and they're easier to make, and as well as, but there are carbon-based rod-like nanoparticles. These, however, have lower biocompatibility compared to some of the spherical nanoparticles. Now, viral nanoparticles, these are things like viruses, and they're often plant-based, and they have the advantage of being very symmetrical and easy to make a ton of them, as well as all of their bonds and everything is well mapped, so this allows them to be researched a lot easier. So the problem that the authors are trying to address is to improve some of the performance of some of these nanoparticles, specifically in the drug delivery and imaging areas. And to do this, they're exploring these filamentous VNPs compared to their spherical versions, and hoping that by using these rod-like nanoparticles, this will lead to the drug delivery improvements that they wanted. And they're specifically investigating these in these plant-derived VNPs. The approach that the authors took was for their rod-shaped nanoparticle, they're using a potato virus X, PVX, and this was grown in potatoes. And then for their spherical version, so that they can get something to compare to, they're using a cowpea mosaic virus, CMPV. And these are both coated with a label, A647. A647 is just a fluorescent tag that corresponds. And this allows them to image them and determine where, in fact, they ended up. And they're also coated with PEG 5000. Now, PEG 5000 is just there so that it allows other things to bond to it, as well as reduces the immune response of the body. In order to test that their VNPs were able to specifically target tumors, they cultured tumor cells and then injected the CPMV and PVX into these cultures and then imaged the cells. So as you can see in the top right, image A, that both of these nanoparticles found their targets. They both penetrated the cancer cells, but PVX, as seen in B, was able to be much more highly concentrated toward the center of the cell. And this is important because that is where a lot of the activity of the cell, and more things can be targeted in that region, like a breakdown of the DNA, for example. And then finally, in the bottom graph, you can see that this is an animal model that they did, where they injected the mice with, they had tumors to start with, and then they injected them with these nanoparticles, and then measured the fluorescence of the nanoparticles after that. So the rod-shaped PVX shown higher concentration in the tumor, as well as a much higher concentration in the spleen, and a less higher concentration in the liver. The liver shows that the spherical nanoparticle was definitely trying to be cleaned out of the blood more drastically than the other one, and then the presence of the rod-shaped cone in the spleen shows that there was more immune response to that cell. So the rod-shaped cells did have enhanced tumor homing and tissue penetration compared to the spherical cells. So they can be used in the future for tissue-specific imaging and targeting, because they were able to directly find what they were trying to go out to. But there was that large presence in the spleen, and this could be related to a large immune response. However, this needs to be further tested. The rod-like structures also have a greater surface area than the spherical ones, so this allows for greater loading of different things. You can fit more cancer drugs, for example, onto the nanoparticle. And also, it hypothetically has a greater area for cell binding, so it can bind to multiple cells on the outside of the cell. But in order to further research these cells, a full biodistribution, so determining where exactly in the body these end up, as well as the pharmacokinetics, and a clearance study how the body gets rid of this new nanoparticle needs to be done in order to really flesh out how to deal with these particles.